Welcome back aspirants on MacTech 40, and today we will solve one derivation that has been asked in ESC mains exam. Okay, so this question is based on a radial flow turbine. Okay, and the data is in a reaction turbine, the radial vents at inlets with radial vents at inlet. This is the important term, and the velocity of flow at outlet is k times that of the inlet. So we have to prove this hydraulic efficiency equation and this runner speed u1. Okay, so very few things are given, and very large thing or very more things that we have to conceptualize and we have to use by our recall memory. So first of all, this is a reaction turbine. Okay, so in reaction turbine, at outlet flow is radial. So what is the flow radial? That means beta 2. The runner blade angle at outlet is 0. Okay, but here radial vents at inlet, that means inlet also beta 1, that means blade angle is also 90° at inlet. And velocity of flow at outlet, again I am telling you, wherever I am using subscript 1, that means at inlet, and wherever I am using subscript 2, it is for outlet. And vf, that means velocity of flow, the component of velocity of jet, which is responsible for discharge. Okay, and whenever I write vw, that means velocity of whirl, and the whirl component is responsible for power production. Okay, so velocity of flow at outlet, so vf2 is k times of vf1. Okay, so we have to prove this. So now here the term h is given to us. H, that is net head. H is net head, and we know the another head, that is Euler's head. So when you add the losses occurred in the system in the Euler's head, then it will become net head. Okay, and when you add the losses in penstock, then it will become gross head. Okay, clear this thing? I'm writing on the next page again this thing, that is Euler's head, that means the actual available head which is generating the power. Okay, Euler's head plus the losses within the turbine and at the exit. Okay, this will become our net head. Net head, that means the actual head or actual the potential energy of water at the inlet of the runner, that is that has the potential to convert into electricity, but due to some losses the total energy could not be get converted. Okay, now in net head, if we add the losses in penstock, okay, so then it will become gross head. So this is the head relation. Now net head h, in our case is h, is equal to, what is the Euler's head? It is vw1 u1 minus vw2 u2 divided by g. Okay, this is Euler's head. Now what are the losses? That means losses due to friction, and the water is exiting the runner or turbine, we can say that, at velocity v2. So the velocity head is also known as v square by 2g, v2 square by 2g. Okay, now here there is nothing mentioned in the question about losses. Okay, so we will neglect this term. Okay, so only term that we have left is vw1 u1 minus vw2 u2 divided by g. plus v2 square by 2g. So this is the net head available at the. Now we will draw the velocity triangles for inlet and as well as outlet. Okay, so for inlet the flow is radial, so there is only the only one triangle and only one angle alpha 1. Okay, and at outlet the flow is also radial because it is a reaction turbine. Okay, so at outlet the flow is like this. Okay, suppose I am drawing a turbine blade here. Suppose this is a runner blade, so this triangle will come over here. Okay, and the flow will strike like this and passes through the blade profile and it will exit. Okay, like this. So this is for your understanding purpose. I'm drawing this both the triangles separately for easy explanation. So this component is absolute velocity at inlet and it is making alpha 1 angle. That means alpha 1 is guide vane angle at inlet. This is u1 peripheral velocity at the outlet because this is the reaction turbine, and generally we are considering here a Francis turbine. So Francis turbine is inward flow turbine. So flow will enter from outer diameter and leave the water at inner diameter like this. So u1 is the outer diameter or peripheral velocity at outlet. Okay, outer diameter, peripheral velocity at outer diameter, and this is vf1, the velocity of flow component. Now here again this is alpha beta 2. Okay, beta 2, and one thing I told you here wrong, that is at outlet if the in reaction turbine alpha 2 is 0, alpha 2 is 90 degree. Sorry, this condition I put wrong here, please correct it. In reaction turbine at outlet the angle made by absolute velocity with the guide blade, okay, is 90 degree, not 0, 90 degree with guide blade, not a runner blade. So this is beta 2 and this is relative velocity vr2, and this vertical component is vf2, and this as this angle is 90 degree alpha 2, so we can also tell this as a absolute velocity, and this is u2, that means peripheral velocity of the runner at inner diameter. Okay, and here u1 is greater than u2, so you can understand here. Now which term we will require? v2. Okay, I'm writing equation here again. Net head is equal to vw1 u1 minus vw2 u2 divided by g plus v2 square by 2g. Okay, now we have h and we require h. We have to find u1 in terms of g and h and alpha 1. So what is vw1? Vw1 is the cos component. Okay, so v1 cos alpha 1 is equal to vw1, but here as you can see that vw1 is same as the u1. Okay, as you can see in the velocity triangle, this is at inlet and this is outlet. Okay, so I can write v1 or u1 as a u1 square because v1 and u1 are the same value. Vw2, that means the component of v2 in horizontal direction making the angle with the peripheral velocity, but v2 is at the perpendicular and it does not have any other component, so this term will be 0. So only we have u1 square by g plus v2. V2 is what? V2 we can say that from figure it is vf2, and vf2 is in the question given is k times vf1, the velocity of flow. So just write K times Vf1 whole square by 2g. Now what is Vf1? Vf1 is from this inlet velocity triangle. You can say that sine, it is a 10 component sine component of V1 and 10 component of U. Okay, so I can write 10 alpha 1 is equal to Vf1 divided by U1. Okay, so I am writing here U1 square by G plus K square into what is Vf1, that is U1 square 10 square alpha divided by 2g. Okay, now I can take U1 square as common, so the head equation will become U1 square by G also common, so 2 plus K square 10 square alpha 1, and here 2 V1 square by 2g, sorry, U1 square by 2g. I have taken U1 square by 2g common. Okay, so here 2 is not here, so we have multiplied here, so this equation will become like this. So we just send this all the value on the other side, so U1 square will become 2gh divided by 2 plus K square 10 square alpha 1, and just take a square root on the both side, so here U1 under root of 2gh divided by 2 plus K square 10 square alpha 1. Okay, so this is the answer of our question. Now we have to also find the hydraulic efficiency. Okay, so hydraulic efficiency in Euler's head term we can find is, we can write is Vw1 U1 minus Vw2 U2 divided by GH. Okay, now but here Vw2 is 0 in our case, so this term will be cancelled out, so only we thing remember here is Vw1 U1 divided by GH. So only thing we have remained. Now from the inlet velocity triangle you can easily say that U1 is equal to Vw1, so U1 square divided by GH, and as you can see here the U1 square has this value, just substitute here, so 2GH divided by GH into 2 plus K square 10 square alpha 1. Okay, inlet guide blade angle, GH will be cancelled out, so we have hydraulic efficiency, we can write 2 times G plus, sorry, 2 times bracket 2 plus K square 10 square alpha 1. So this is the answer of our the second thing that they have asked. Okay, so here we have found both the things. If you have still any doubt, you can ask in the comment section, we will solve in a next video. The main thing, the main concept of this, from where to start, this is the important thing. The then all the things are very easy, you can easily solve, but the main start is from where to start. Okay, so the start point, the main conceptual point is this, the different head. Okay, and how to implement this all the head in equation form. Okay, hope you guys understand. So tomorrow we will solve another question of the similar kind. Till then, keep studying, stay focused.